Today we're going to dive into the story behind one of the most iconic charts in all of science, the periodic table. I mean, you've seen it everywhere, right? In classrooms and labs, probably on a t-shirt or two. But it is so much more than just a poster. It's a story of discovery, a puzzle that took decades to solve, and it's basically a map to the building blocks of our entire universe. So let's get into the quest to understand the hidden order behind all the elements.
The great chemist Glenn T. Seaborg really just hit the nail on the head here. The key idea, the thing to hold on to, is that the elements are not a random jumble. For centuries, it really seemed like they were, but there was this hidden order just waiting to be found. This quote, it really sets the stage for our entire story, the search for a pattern in the chaos of creation.
Okay, so let's set the scene. It's the 19th century. Chemistry is absolutely booming, and scientists are discovering new elements left and right. Now, this was super exciting, of course, but it created a huge problem. This growing list of fundamental substances was becoming a total mess. How could anyone possibly make sense of them all?
So back in the year 1800, the whole situation was, well, it was still kind of manageable. We knew about 31 chemical elements. It's a bit of a crowd, sure, but you could still keep track of them and their properties without going completely crazy. But as you can probably guess, this was just the beginning.
Now, let's fast forward just 65 years to 1865. The number of known elements had more than doubled to 63. The list was getting seriously out of hand. I mean, can you imagine trying to memorize 63 completely separate things, each with its own unique personality and behavior? Scientists knew there just had to be a better way, some kind of system to organize this elemental library. And so, the search was on. A few brilliant minds started to notice these faint glimmers of a pattern in all that chaos. Now, these early attempts, they weren't perfect, not by a long shot, but they were the absolute crucial first steps on the path to the periodic table that we all know and love today. One of the very first people to see something was a German chemist, Johann Dobereiner. We're talking the early 1800s here. He was really the first to take the idea of trends seriously, noticing that some elements seem to come in these little families of three, which he called triads. So what's so cool about these triads? Well, take a look. If you take lithium with an atomic weight of 7 and potassium with an atomic weight of 39, and you find their average, so 7 plus 39 divided by 2, you get 23. Well, what's the atomic weight of sodium? Exactly 23. This was a mind-blowing clue. But since it only worked for a few families, a lot of people just dismissed it as a quirky coincidence.
All right, next up in our story is an English chemist named John Newlands. In 1865, he brought a little bit of music into the world of chemistry. He came up with the law of octaves, suggesting that when you arrange the elements by their atomic weights, their properties seem to repeat every eighth element. Just like the notes in a musical scale.
You can really see what he was thinking right here. He lines them up. Lithium is the first, and then the eighth element over is sodium, and we already know from Dobereiner that they're super similar. The ninth, magnesium, lines up with the second, beryllium. It was another brilliant insight, right? But the pattern totally fell apart after calcium. So his idea wasn't really accepted at the time, but man, he was getting so close to the truth.
And that brings us to the hero of our story, the Russian chemist Dmitri Mendeleev. Where other people saw little pieces of a pattern, Mendeleev saw the whole grand design. He's the one who gets the credit for creating the first truly workable and even predictive periodic table. This was Mendeleev's guiding star, his periodic law. And just like the others, he arranged the elements in order of increasing atomic weight. But here was his stroke of genius. He insisted that elements with similar properties must fall into the same vertical columns or groups no matter what. That was the rule that changed everything. And this is what made Mendeleev a legend. He was so sure of his system that when the next element in line by weight didn't fit the properties of a column, he did something incredibly bold. He just left a blank space. He actually predicted that an undiscovered element would one day be found to fill that exact gap.
And this table just shows his incredible foresight perfectly. For instance, he left a gap below aluminum, and he called the missing element Eka aluminum. He predicted its atomic weight would be around 68, and its density would be 5.9. Well, years later, gallium was discovered, and its actual atomic weight? Almost 70. He was spot on. And its density? 5.94. The accuracy was just stunning. It proved his table was the real deal.
Mendeleev's table was, without a doubt, a monumental achievement. But there was a twist in the tale. His organizing principle, atomic weight, was a really, really good approximation of the truth, but it wasn't the final answer. There was a deeper, more fundamental secret still hiding inside the atom itself.
See, Mendeleev's system wasn't perfect. There were a few little nagging problems where he actually had to break his own rule. Take this one, for example. He placed iodine after tellurium, even though iodine actually has a slightly lower atomic weight. He did it because he just knew, based on its properties, that iodine belonged in the same family as chlorine and bromine. He knew it was the right move, but he couldn't explain why.
The final piece of this huge puzzle came in 1913 from a young English physicist named Henry Moseley. By studying X-rays, he found that the true defining feature of an element wasn't its weight at all. It was its atomic number, the number of protons in its nucleus. This was the element's fundamental identity, like a unique barcode for every single one.
And with Moseley's discovery, the law got an update. The modern periodic law says that an element's properties are a periodic function of its atomic number. As soon as the table was reordered using this new principle, all of those little inconsistencies, like the tellurium-iodine problem, they just vanished. The puzzle was finally completely solved. So, with the incredible story of its creation now told, let's take a look at how to decode this modern map of matter. Because it's not just a collection of boxes, it's a tool that is absolutely packed with predictive power. First off, that kind of weird shape of the table, it's not random at all. It's a direct reflection of how electrons fill up their shells, or orbitals, around an atom's nucleus. This electron configuration, especially the way the outermost electrons are arranged, is the ultimate source of an element's chemical properties. It's what dictates how an atom will bond and react with everything else.
So let's cover the basic geography real quick. The horizontal rows are called periods. As you move across a period, you're adding one proton and one electron at a time. The vertical columns? Those are called groups. And here's the most important rule of all. Elements in the same group have similar setups for their outer electrons, and because of that, they behave in very, very similar ways.
And because of this amazing structure, these beautiful patterns emerge. Properties like an atom's size or its reactivity, they change in a really predictable way. For example, as you go down a group, the atoms get bigger because you keep adding new electron shells. But, and this is a cool one, as you go from left to right across a period, they actually get smaller. Why? Because the growing number of protons in the nucleus pulls all the electron shells in just a little bit tighter.
So when it comes right down to it, the magic of the table is this. An element's position, its address on the map, isn't just a random label. It's a summary of its entire identity. It tells you its atomic structure, it predicts how it's going to react with other elements, and it reveals its deep relationship to all the other building blocks of the universe.
That whole quest for order that started with Dobereiner's little triads gave us this incredible map. But the story isn't over. Scientists today are still pushing the boundaries, creating brand new, super heavy elements in labs. Which leaves us with a pretty fascinating question to think about, right? What new residents will be adding to this table, and what secrets are they going to reveal?